So we are learning state space models, but before starting today's lecture, I have to re-announce this. So next Monday we have quiz 2 and no electronic devices allowed, but it's open book test. Okay. So you can bring any paper materials, but no electronic devices is allowed. Okay. And next Wednesday we don't have any class. Okay. So and also the next week, spanning 2 class, we will have final term project presentation. Okay, final presentation for the final term project. Okay. Presentation. So you need to submit the 7-minute video by this date to me, same as before. Okay, so please use the web storage. Don't use the YouTube. Okay, so we have to download your video. So don't use YouTube, but use some storage device to send the video. Okay. So this is all. Okay. So and this is actually the last lecture of this class. Okay. So we have learned transformer and how transformers are applied to the image classification. So that's the vision transformer, and slightly improved version of VIT has been introduced, such as the swing transformer or gate. Okay. And also I explained this SSM, which is the state space model. Okay. So RNN, CNN transformers, they are good at capturing long dependencies, but it's not able to capture the very long dependencies. Okay, so SSMs are promising to capture such long dependencies when matrix A is properly set. So this is the SSM, their continuous version of formula. When their A matrix is properly set, then they can capture long dependencies. But it is hard to secure their, hard to secure their computation and memory requirements, so that it is actually very hard to implement that in the real hardware. So that was the hurdle for that. Okay? But this paper I said they are providing some possibility of applying SSMs in real implementation by discretizing the signals. Okay, so because we indeed use the discrete input and output variables for the deep architecture. So actually, from this continuous signal, we can sample with some offsets. That is the delta here. They define delta and sample the input signals, and also so this U and Y, they become discretized, and at the same time the hidden state X also becomes discretized, and also A and B, C and D matrix, they are updated, okay, to deal with this discretized inputs. And I also say you that this operation, when discretized, we can interpret this whole process could be interpreted as convolution operation. So previously, we had to calculate this recurrently. So from U0, we have to calculate X0, and from X0 and U0, we have to calculate Y0, which is the first inputs output. Okay, and then we calculate sequentially the next X1, and Y2. Okay, so sequentially only we can calculate the output. Okay, one by one. If we are given this kind of the differentiable equation, then we have to calculate it one by one. But actually, this is showing that if we calculate it one by one, And then we can generally represent the output yk according to several input. Okay, and then we can interpret this formula as the convolution operation between input u and the filter kernel k. Okay, so and we have to define these filter kernels as this. Okay, so the convolution operation can be calculated parallelly. So I mean, instead of calculating all the outputs sequentially, we can parallelly calculate the output using the convolution operation. So that is actually induced from this structured SSM paper. And after that, I mean, there could be some possibility for implementing this SSM in the real hardware. And after that, this Mamba is appeared. And actually, this figure is representing this discrete version of SSM. So I will explain that. So now our H is the hidden state, and here X is our input. Okay, so say HT is equal to A bar HT minus 1 plus B X of T. So here the notation has been slightly changed. Okay, so I mean, originally we told that UK is the input signal and X is hidden state and Y was the output. But Y is still representing the output, but we changed it, the notation. So I mean, this could be confused, but I mean, this is more intuitive. So we will change the notation. So X now is indicating the input, and H, this is indicating the hidden state. Okay, and so hidden state, their values are updated from the previous layer's hidden state. Okay, this is HT minus 1, which is the hidden state values from the T minus 1. I mean, the previous time. Okay, and this is coming from the previous layer, and this is the new input. So we multiply A bar matrix to the previous hidden state and add the current input by multiplying it with the B bar matrix. And somehow we are updating the hidden state at time t, and then multiplying the C bar matrix to the current hidden state, we can get the final output. Okay, so this is visualized here. So this is the HT minus 1, the hidden state from the previous time, and we multiply A matrix, and for calculating this H of T, we multiply A matrix to HT minus 1. At the same time, multiply B matrix to our current input, and we will add that to this string. Okay, so this is representing this part is representing A HT minus 1 plus B X of T. Okay. And also, this becomes our current hidden state. At the same time, the same output is going through this multiplication of CT matrix, and then output the final output Y. Okay, so this is actually, you can feel that this figure, entire figure, is representing this original structure SSM formula. Okay, so this figure is representing that. But there are one difference in this Mamba architecture. So this is actually the advanced version of this S4 network. Okay. So S4 structured SSMs, they are mentioning that this by discretizing the continuous signals and by interpreting this operation as the filter convolution, they can be efficiently calculated. That's the structured SSMs. But in Mamba, there are a few more improvements. So that's basically they are using the same discretized formula, but they have one more scheme, which is the selective method, selection method. So, I mean, so because of that, the Mamba is called as selective SSMs, okay? And basically, this kind of operation is the linear operation, okay? Linear operation generally can solve most of the problems, but if the problem becomes more complex, then there are sometimes the problem appears which is not solved by this linear operation. Okay, so to solve that, actually, this kind of selective mechanism, the selection mechanism, have been added to the S4 architecture. So that's the Mamba architecture. So linear time sequence modeling with selective state spaces. Okay, that's the Mamba model. New promising architecture that can replace the transformer. So in this project, in this projection, what they do is actually important. Previously, we used the same A and B and C metrics for all the XT and HT signals. I mean, no matter their T variable, I mean, regardless of this T variable, they are using the same ABC matrix, okay? But in the Mamba, they are actually generating the B matrix and the C matrix according to the, according to the X of T, okay? So now you can realize that this A and C, this B and C matrices are becoming different depending on the input signals, okay? And also A is also affected because when calculating A, maybe A is same, I'm not sure. Maybe A remains same, but B and C becoming different, okay? Anyways, these matrices are becoming different depending on the X of T. That's the difference, okay? And also this offset variable, this offset was used as the constant before, but it also changes according to the X of T, which is the input variable, okay? So now this kind of selection mechanism has been added to the normal S4 architecture, and that is actually the Mamba architecture, okay? And this is showing the difference between LTI operation, linear time invariant operation, and actually time varying operation. Okay, so previous S4 is LTI, which means their ABC matrices are different, remain same regardless of their input. Okay, so we can interpret their this formula as a totally linear operation, but in Mamba, their B and C matrices are becoming different, becoming different depending on the input signal. So we can say they are becoming time varied. Okay? So in terms of efficiency, actually, this S4 is more efficient. Okay, so but I mean, this Mamba can solve some complex problems that where the S4 is suffering from. So we are using this kind of Mamba architecture. So for example, this is the copying operation. So let's say this is the input sequence. For example, the NLP, I mean sentence, word sequence. We can exemplify this as the word sequence. So each block is denoting the word in the sentence. Then, I mean, for example, when doing copying, uh, the output sequence, we have to calculate, I mean, we have to copy some of the consecutive words, okay? In this kind of simple copying problem, this LTI operation is efficient and they can be easily solved this kind of copying problem. But the Mamba authors are saying that if they are applied to the selective copying, for example, if they're, I mean, this kind of word, if they are involving some unnecessary or blank word in between, but if we still want to copy some of the key word in the sentence, then this kind of S4 architecture having the LTI characteristic is suffering. So they cannot achieve this kind of thing. So, I mean, to solve this kind of selective copying, depending on each x of t, depending on each input, the A, B, C matrix in the original formula uh, have to be maybe changed, okay? So depending on the x, uh, depending on the certain input, we have to, I mean, strength or weakening the, I mean, the scale of the B and C matrices, okay, to adaptively control the input contributions of the input signal, okay. So actually, that is the, I mean, motivation of this Mamba to have this kind of selective mechanism, and also this kind of induction problem. So when given this kind of sequence and doing some induction, so I mean, this is the problem saying that what block have to be, what word have to be located here if this kind of black word has been appeared, okay? So in that case, we have to, I mean, search for previous history and find the case where this block has been there, and in the next word, what word has been come, okay? So this kind of inductive problem, also they are saying this kind of time varying mechanism, the selection mechanism is more helpful, okay? So that's why the Mamba is having this kind of selective mechanism. So this is the S4 architecture, and we are having this Mamba. Its name is also called as S6. Okay. So previously, this ABC matrix, A is retained, same as before. Okay, but B and C matrix now, previously it has the constant value. Okay, but now B and C, they are changed to have the same dimension with the input and output dimension. So B is the batch size. This is the batch size. And L is the length of the word. Okay. So this D is the dimension of the word vector, maybe. And X and Y, they are having the similar dimension. But previously, this dimension is not coincide with B and L. I mean, their B and C was constant for every input. So they don't have, I mean, B and C, we don't have to store B and C for each input, but now we have to change the schemes to have the separate B and C for each input. Okay, so that is changing. So, and this is indicating the network that is estimating this B and C network. Okay, and X is the input. So we actually, depending on the X, which is the input, we estimate the B matrix and also the C matrix. Okay. And also the delta, well, which was the actually constant in our case. We previously it was the constant, and that is actually the offset for sampling. But now we also change this offset value depending on the input. So, for example, when this input comes, our offset becomes this kind of 3. So we have to, skip this 2 word and then sample the next word here, okay? And now the offset have to be 1, and then offset have to be wider in this case. So this kind of sampling is also controlled by this offset, and they are now becoming the variable instead of the constant, okay? Okay. So without this, most of the things are same as the S4 as visualized here as well. Okay, but now Mamba having the different B and C and this offset variable depending on the X of t, which is the input signal. So that is the main difference. So previously, S4 was time invariant architecture, but now the Mamba is becoming input dependent architecture. So as far as I understand, the effectiveness, efficiency is becoming less compared to the S4 architecture. The Mamba is losing something because of this B and delta BC matrix and delta to make it dependent on the input. They are losing some good characteristics, which is the time invariant characteristic, but they can obtain better characteristic that can make this kind of ability to solve the more complex problems. Okay. And also Mamba is having, this was the original backbone architecture. Okay, so actually this is the SSM operation. We are studying this here, right? So this SSM is one of the blocks inside of the overall architecture. And this H3, that is actually, the main backbones, for the SSMs in deep architecture. But in Mamba, they are combining some good characteristics of this gated NLP. And Mamba, they constitute their Mamba operation like this. Okay, so this gated NLP, you can think this as the like the LSTM operation, which can adjust the forget and information bit to control how much they want to forget or how much they want to retain the information. Okay, so in LSTM we have explicit bit to control each information, how much we want to forget or retain. So this stream is doing that kind of thing. And actually H3, there was not gated operation before, but in Mamba, we have this kind of stream at the same time having the gated MLP layer to control, to control how much information we will retain or forget. We want to somehow learn such things. Okay, so this is also, advanced component in the Mamba architecture. Okay, so in SSM component, we can say this kind of selection mechanism has been added. And in overall architecture, this kind of gated operation has been added. So that's the Mamba. Okay. And so in Mamba, so they are becoming promising in NLP domain. Actually, they are replacing the transformer architecture nowadays. Okay. But there has been some, attempt that try to use this Mamba architecture in the computer vision domain as well. So similar to the transformer, when their results are promising in NLP domain, the computer vision researchers are trying to involve those new architecture in the computer vision domain as well. So this Vision Mamba was the first paper that does that kind of approach. Okay, and this is actually very simple. If you, remind of the VIT, which is the extension of transformer towards the vision domain. Similar to that, you can understand this Vision Mamba as similar to the vision transformer, which is the VIT. So input image, from the input image, you divide the overall images into some of the patches, okay? And then you can now interpret each patch as the, word, somehow word, okay? In sentence, in NLP domain, the inputs are mostly sentence and they are composed of multiple words, okay? But images, those are composed of multiple patches. So this is intuitive to divide the overall images into patches, okay? And supply those patches into the this Mamba encoder, okay? So each input becoming the patches, okay? But the only difference in Mamba, so this architecture is actually similar to the one in here, okay? But the only difference is in SSM, they try to involve bi-directions. So in Mamba, you already know that their formula looks like this: t minus 1 plus b x of t becomes some new hidden state. And if you multiply c, then we can obtain y of t. And then you can propagate this to the next stage and do the same thing to get the next time output, okay? So they call that as the forward process, okay? But they have the opposite directional operation, and we will call that as the backward process here. So maybe this becomes the next time signal, and this becomes the previous time signal in backward stream, okay? So in the Vision Mamba, their motivation is because we are dealing with image signals which doesn't have any sequential meaning. But in the sentence, in the NLP domain, the previous word is actually having the meaning, the order of the word. For example, I am a student. Here, the order is actually important. And because of that, they only have the forward process inside the NLP Mamba. But in the image domain, actually there's no orders in image patches. So they are somehow insisting that having the backward stream is important, okay? So, and they are actually extending the original Mamba to have the bi-directional process, okay? So forward and backward. So that's the Vision Mamba, what this ICML paper is insisting, proposing. So efficient visual representation learning with bi-directional SSM. Okay, that is the Vision Mamba. Okay. The only difference is this having this backward process. And compared to the date, which is the one of the Vision transformer variant, okay, you can see that their classification and detection and segmentation performance is becoming better than the VIT. Okay, so and also it is become the in the speed wise also the Mamba is efficient. Okay, and memory also Mamba is not consuming much memory compared to the VIT as well. So you can see this Mamba is also very promising in computer vision domain as well. Okay, and also this is the I mean comparison with and without the bidirectional strategy. Okay, so if there is no bidirectional strategy, then for this ImageNet, their performance is not that I mean essential. Sometimes without even without bidirectional skins, this unidirectional strategy also exhibits good accuracy, but especially in this kind of more challenging data set, we can see there are a lot of performance improvement. So, this is the way the authors of this Vision Mamba is saying this involving bidirectional component is effective in vision tasks. Okay, and there have been another approaches that try to involve these Mamba architectures inside the computer vision community. So that's the V-Mamba. So the name is very similar, but their paper name is Visual SSM, okay, and published in Europe last year. And their method is quite simple, and this SS2D is the most important contribution of theirs. So compared to the self-attention that for given one query patch, they have the dense, dense dot producting between two patches. This SS2D is actually interpreting, reusing the original S6 blocks, which have this kind of differential equation, okay, to calculate Y from the Xn hidden state, okay. We are involving the same architecture as the Mamba, but because we are dealing with image domain signals. So their idea is having this kind of scanning, proposing 4 different scanning methods. So in this direction, they retrieve the images into 1 to 3 to 9 patch. And this direction, also they can scan the patches. And in different directions, they can also scan the patches, and this is also another way to scanning the patch, okay? And then they interpret these patches as the sentence or one-dimensional signal having the order, and apply the original Mamba, okay, that can deal with 1D signals, and also do apply this with different scanning methods. And then after applying this S6 block, there are multiple outputs coming from these 4 different scanning, and then they merge their activations to make the output patches. Okay, that's the core idea of this V-Mamba. And actually this SS2D is now widely used compared to this bidirectional method, and subsequent work is using this kind of SS2D mechanism more frequently. Okay, so using that, this VSS block is having this kind of SS2D mechanism, And this is the overall architecture of the V-Mamba. So given input image, they divide the patches and apply VSS block multiple times to get the final output. So this is the V-Mamba architecture. And they also compared, this is the original Mamba block, and this is the VSS block they are proposing. And they are only replacing maybe this S6 with the SS2D, then this vanilla VSS block is somehow weak. So they are proposing this VSS block. So there are two residual blocks here. So some architectural changes have been made. Okay. So anyways, this VSS block, having this SS2D operation is used in the entire architecture. That is the V-Mamba architecture. Okay. And also there has been some, approaches that apply this Mamba architecture explicitly for the object detection task. So the paper of this is called as Mamba YOLO, and that is published in AAAI this year. And so they are composed of three architectures, three main layers. And this simple stand that is actually dividing the images into patches, and this vision clue merge, they are basically does the downsampling operation. And this ODSS block, that is the block involving the SSM mechanism, and that is actually highlighted here. Okay, so I will explain it after explaining this part, but their main component is also SS2D, which divides, does the scanning in 4 different ways and apply the same SSM as the S6, and then merge those activations. Okay, so anyways, they are involving this ODSS block as their main component. Okay, and vision clue, you can think of that as the downsampling. Okay, and also after applying this ODSS block for entire image, they are actually separating into 3 different scales. Okay, and then they eventually predict 3 different scaled output for the object detection task. And also in the middle, this U is indicating the upsampling, and down is indicating the downsampling, and C is indicating the concatenation. So this is the high-level feature, but when applied with mid-level features, and they upsample that and concatenating with the high resolution feature and apply ODSS block. Okay, and anyways, they are somehow mixing the high resolution feature with the low resolution feature, and eventually make 3 different scaled features and apply the final predictor, final head, to predict the bounding box and segmentation and classification losses. Okay, so this is the Mamba YOLO architecture, and this is their core as ODSS block. Okay, object detection state space block. And here as well, the SS2D is the main block. Okay, but they are having some pre-processing and also having some post-processing, and this is called as residual gated block. Their actually motivation is this path is having some global information about the input, but by applying this kind of convolution, they can extract some of the local information, and they are combining that to, get the final output. Okay, so this is the Mamba YOLO architecture actually. So this RG block is applied after the SS2D operation and get the final output. Okay, and using this ODSS block as the main block, this is the entire Mamba YOLO architecture. Okay, and this is the performance comparison to YOLO and others. And you can, I mean, this is indicating the how to say, the latency, the speed, and this is indicating the accuracy. Okay, so this Mamba is showing the best performance at the same time showing the best speed. Okay, so even better than the recent YOLOs. Okay, and this is another comparison. Okay, so this is actually the end of this lecture. Okay, so I mean, here, I mean, we can see how the recent architectures, the Mamba, has been applied in vision domain, and also learn about their core algorithms. So yeah, that's it. Okay, so this is end of today's lecture, and maybe see you next week, Monday, and there's quiz 2 in Monday. Okay, thank you. See you on next Monday.